Hello students, hope all of you are well. So today we are going to discuss the second topic of the introduction to the partial differential equation, that is the formation of partial differential equation by eliminating arbitrary function. So if you have not visited the previous video lecture, please visit it, because there we have given the information about the formation of partial differential equation by eliminating arbitrary constant. So here we are going to do for the arbitrary function. So let us start. So before we are going to derive the problem and its solution technique, let us try to understand the difference between two type of structures of a given function. One is known as the implicit function, another one, the representation, is known as the explicit function. So what is an implicit function? That if the dependent variables is written directly in terms of independent variables, then the form is known as an explicit representation. That is, the dependent variable, suppose it is z, and it depends on two independent variables x and y. So if z is explicitly written in terms of x and y, where z is written on the left hand side and rest of the terms we can write down on the right hand side, so this type of representation is known as the explicit representation of a function. Now there is another representation which is the implicit representation. So what is an implicit representation? If the dependent variables and independent variables are mixed up, mixed up together, we cannot be isolate them. So z cannot be isolated and cannot be written in the structure of function of f of xy easily. We can write down, but that cannot be done very easily. So such type of representation is known as an implicit representation. So in our exam we can have both types of representation of type of function, both type of function. So first of all, if the structure of the function is given in terms of the explicit form, the solution technique will be much more easier compared to the implicit form. So here I have written the structure for the implicit function, and I have done the problems for both types, that is explicit form and implicit form. But this type implicit form is little bit difficult, so that's why we are trying to understand the scenario. Suppose we are having a function phi of u comma v equals to 0. So this is the implicit representation of a function where u and v are functions of x, y and z. These two are different functions, and z, which is depending on two independent variables x and y. So we can see inside u x, y, z all present, inside v also x, y, z all present, and inside z x and y all present. So this type of representation is nothing but the implicit representation. Now the phi is the unknown function that we have to eliminate from this relation to form the partial differential equation. Before we are going to take the partial derivative, let us try to understand the chain rule of such kind of differentiation. So here if I write down, then we can see that phi is basically directly depends on two functions. One is u, another is v, right? So but u is depends on x, u depends on y, u depends on z directly. Similarly, v depends on x, v depends on y, and v depends on z. Similarly, if we just more expand it, so z depends on x, z depends on y, and here also z depends on x and z depends on y. So if we have to apply the differentiation of phi with respect to the independent variables x and y, so we have to do lot of steps here. So let us try to understand how to do the partial derivatives on phi function. So as I have mentioned here, that's like the tree type of structure. So if I want to take the differentiation of phi with respect to x, I cannot do it directly, because phi to x, here we are having one intermediate step, that is u. So I cannot jump from phi to x directly. I have to stop at u first. So phi with respect to u. Now inside u we are having lot of more structures. So u with respect to x, this can be done directly, but here also another x is present, that is inside z. So u to this x is not also possible directly. quickly. So what we have to do, we have to come from u to z first, thereafter z to x. So this will be the scenario. So phi to u, u to x, u to z, and z to x. So that I have written here. So first of all, phi with respect to u, that is del phi del u. Now we are going inside the function u. So u with respect to x, since it is a direct relation, we can do it directly, del u del x, plus now u depends on z, z depends on x, so del u del z into del z del x. So one part or one side of the differentiation we have done. Same thing we have to do for v also, right? Because phi depends on v, v depends on x, v depends on z, z depends on x. So same type of structure, phi to x on the right hand side. First of all, we have to take the derivative of phi with respect to v. So del phi del v. Now we have to go inside the v function. Inside v function we are having x, y and z. So del v del x can be done easily, plus now del v to this x we have to stop at z, so del v del z into del z del x. So this is the differentiation of phi function with respect to x. In a similar manner, we can do the differentiation of the phi function with respect to y. So we will have the form, same form, only you can understand that x has been replaced by y. Now we have to eliminate phi, right? So in equation 2 and equation 3, where phi is coming? In this coefficient term, del phi del u, this is del phi del u, here also del phi del v, and here also del phi del v. Now how to eliminate this? We know from our determinant or concept, that is we have learned in our class 11-12 while we have finding the solution of the linear homogeneous equation. So that can be find out by just making the determinant of the coefficients of del phi del u, del phi del v equals to 0. So the coefficient of del phi del u in the equation number 2 is del u del x plus p del u del z. Why I am writing p here? P represents by del z del x. Last class I have already mentioned this. Similarly, del v del x plus p del v del z of the coefficient of del phi del v. Similarly, the coefficient of del phi del u with respect to y and del phi del v with respect to y we have written here. So after simplification of the determinant, just making the cross multiply and rearranging the terms, we are having one equation in the structure, capital P into small p plus capital Q into small q equal to capital R, where capital P, it is nothing but a function of x, y as well as z. Capital Q is also a function of x, y as well as z, and R obviously another function of x, y as well as z. Okay, so this is the differential equation that we want to receive. Now let us come to do some examples to understand the fact behind it. So now first of all we are going to explore for the type 1 problem, that is for the explicit form. Okay, so for explicit form, just I have told you that the dependent variables are explicitly written in terms of the independent variables, right? So now for example 1, it is says form the partial differential equation by eliminating f from the relation z equals to f of x square plus y square, where f is our unknown function, we want to eliminate it. Okay, so say this is our given equation, we put it as equation number 1. So now we want to differentiate equation 1 partially with respect to x. So left hand side we have del z del x. F function, we have no information about f function. It can be sine, cos, it can be tan, it can be trigonometric, it can be exponential, logarithmic, any kind of function it can be. So what we have to write down here, differentiation of f with respect to x, we will simply write it as f dash of x square plus y square. But inside function, if we look, we are having two terms, x square plus y square. So this term we have to differentiate. X square differentiation is 2x, y square differentiation with respect to x, that is completely 0. So this is the differentiation of z partially with respect to x. Similarly, if we differentiate partially with respect to y, what we have, del z del y equals to same way, that is f dash of x square plus y square multiplied with differentiation of y square only it will come, because with respect to y, x square differentiation is going to be 0. So now if you remember the notation, so as per the notation we can write it as p equals to f dash of x square plus y square into 2x. Similarly, from here q equals to f dash of x square plus y square into 2y, right? Okay, so now what we have to eliminate, we have to eliminate f function. So from this two term you can very easily understand that f dash of x square plus y square, basically from the first equation, say this is equation 2 and say this is equation 3. So from 2 what we can write down, f dashed value, that is equals to p upon 2x, right? Similarly, f dashed of x square plus y square, this value from equation number 3 we can write it as q upon 2y. Since both are the same function, therefore we can write it as p upon 2x equals to q upon 2y. So our final answer is py minus q, sorry, it will be small only, so I have to remove it. So py minus small qx, this is equals to 0. So you can see the structure is coming capital P into small p plus capital Q into small q equal to capital R. So this is the differential equation that we are receiving here. Let us come to the next problem. Form the partial differential equation by eliminating f from the relation z equals to x into y plus x square plus y square plus z square. Okay, same thing, say this is the given equation, we put it as equation number 1. Now differentiating equation number 1 partially with respect to x. So we have del z del x equals to, what is the differentiation of x into y? Here with respect to x, if I differentiate, it will come y only, plus about f function we have no information, so we have to write it as f dash of x square plus y square plus z square. Now we have to go inside x square plus y square plus z square. So what we will have, x square differentiation is 2x plus y square differentiation is 0, but inside z x and y both present, so it will be 2z del z del x. Okay, similarly if we differentiate partially with respect to y, what we have, del z del y equals to x plus f dash of x square plus y square plus z square multiplied with, inside if we go of f dashed function, we are having x square plus y square plus z square. X square differentiation with respect to y is 0, y square differentiation is 2y plus z square differentiation 2z del z del y, right? So now let us try to rewrite equation number 2 and equation number 3. So we will be able to understand how we can eliminate f dashed function. So del z del x can be written as small p. So small p you can take minus y on the left hand side, and you can write down it as f dashed of x square plus y square plus z square 2 times of x plus 2 times of z into p, right? Similarly here from the equation number 3 we can write down q minus x equals to f dash of x square plus y square plus z square 2 times of y plus 2 times of z into q. Now how to eliminate this f dashed function? Obviously now it is in front of you. So from first one you can write down f dashed of x square plus y square plus z square equals to p minus y by 2x plus 2zp. So from here we can write down f dashed of x square plus y square plus z square. This is equals to p minus y upon 2x plus 2zp. Similarly from second one, f dashed of x square plus y square plus z square, this can be written as q minus x upon 2y plus 2zq. So simply you have to equate these two, right? You will get the differential equation. So our final answer, it can be written as p minus y upon, I am just cancelling 2 from the denominator because both are going to be same only. So x plus zp, this can be equate with q minus x divided by y plus zq. So you just cross multiply this. So p minus y multiplied with y plus zq, this is equals to q minus x into x plus zp. You can leave your answer here, or you can rearrange it something into small p plus something into small q equals to some other elements. Okay, just you have to open the bracket, multiply and take common p, take common q, and rest of the terms on the right hand side. So that is going to be your partial differential equation. Now let us come to discuss about the implicit form, which is very important for our exam. So now suppose we are having the partial differential equation from where we have to eliminate phi, and the form of the function is given in terms of the implicit structure. So here we cannot eliminate or write down z in terms of x and y very easily. So the function is given by phi of x square plus y square plus z square, lx plus my plus nz. L, m, n are constant terms. How to approach to this question? Whatever will be given inside phi function, remember this, we have to consider these two terms as two new variable. So first term we are considering it as u, second term we are considering it as v. So u equals to x square plus y square plus z square, v equals to lx plus my plus nz. Therefore phi of uv equals to 0. We are giving it as a equation number 1. So now we have to differentiate 1 with respect to x. As I have mentioned earlier, the structure of phi, it depends on two variable u and v. U depends on x, y as well as z. Z depends on x as well as y. The same type of scenario will happen for v also, right? So this structure we have to do. Phi with respect to x means first phi with respect to u, then u with respect to x, u with respect to z, and z with respect to x. So this form already I have written just at the beginning of this video. So now using this form, if we have to proceed it, say we have to do the differentiation now inside the terms. So del phi del u, I don't know the phi function, so del phi del u will be as it is, but I know the structure of u. U equals to what? X square plus y square plus z square. So del u del x is going to be 2x plus del u del z, that is going to be 2z, and del z del x is symbolized by p, plus what we can have del phi del v del x. So if I differentiate partially with respect to x, we have L here, plus del v del z, it is going to be n here, and del v del z del x, that is equals to p. This is equals to 0. Similarly, if we differentiate with respect to y, what we are having here, del phi del u del y. So what is our del u del y? what is our del u del y? That is equals to 2y, right? So here del phi del u will be as it is. Del u del y is 2y plus del u del z is 2z. Del z del y is our q plus del phi del v multiplied with del v del y, that is equal to our m, plus del v del z, that is equal to n, and del z del y, that is equal to q. So say this is our equation number 2 and this is our equation number 3. So how to eliminate this phi function from 2 and 3? Simply we have to use the concept of the determinant. So the coefficients we have to write down here. What are the coefficients we have? Del phi del u from this one, that is 2x plus 2zp. Here L plus NQ, NP. Here we are having 2y plus 2zq. Here what we are having? M plus NQ. So we have to just cross multiply and write down our final answer, right, to break its determinant. So we have here 2 we can cancel out. So x plus zp multiplied with m plus nq, right, minus L plus NP multiplied with 2 is already cancelled out, y plus ZQ, this is equals to 0. So you just open the bracket, let it just multiply, cross or do the simplification. Final answer, it is going to come ny minus mz into p. I am just taking the p common. Thereafter the terms with q, that is lz minus nx into q. Rest of the terms I am taking on the right hand side. So this is going to be mx minus ly. So this is our desired partial differential equation. Let us come to the next problem and the last problem of today's lecture. So now similarly we have to eliminate phi from the given to form a partial differential equation from the given relation, that is phi of x square y square plus z square and z square minus xy. As I have told you already, two terms are there. So first term you have to consider it as u, second term you have to consider it as v, right? So u equals to x square plus y square plus z square and v equals to z square minus xy. Phi of ub equals to 0. That is equation 1. Now differentiating equation 1 with respect to x, same structure, same formulation. So here I have to differentiate it. So del phi del u will be as it is, since I don't know about this function phi. Del u del x, it is going to be 2x plus del u del z, it is going to be 2z p plus del phi del v will be as it is, del v del x. So this is going to be what? That is minus of y plus del v del z, this is going to be 2z, and del z del x, that is p. This is equals to 0. Say this is equation number 2. Similarly, let us differentiate the second one with respect to y now. So del phi del u will be as it is, del u del x, it is going to be 2y plus 2zq plus del phi of del v del y. So this is going to be minus of x plus del v del z, this is going to be 2z, and this is going to be q. This is equals to 0. So simply we have to substitute all these things to get the differential equation from the coefficients here. So eliminate phi from 2 and 3. We have 2x plus 2zp and minus y plus 2zp, and here 2y plus 2zq, and here minus x plus 2zq. So now just cross multiply, break this determinant to write down the final answer. So here 2 is coming in all the terms, here 2 is coming in all the terms, just like the previous question. So this 2 can be cancelled down, and we have here x plus zp multiplied with minus x plus 2zq minus of minus y plus 2zp into y plus zq. This is equals to 0. On simplification, you will get the final form of the equation, or you can leave it here. There is no problem. So up to this, today we have done. Next video lecture, I am going to start with the non-linear first order partial differential equation and its types with the classification. Thank you all.